Me dijeron que diera el seminario en inglés. ¿Está bien? Okay. Okay, so good afternoon, everyone. Thank you for coming. As Joel introduced me already, my name is Samantha.
Oye, yo creo que tu micrófono está apagado porque no se ve.
Okay. Oh, maybe if I hold it. Yeah, okay. Yeah, so I'm working at the... Ooh. O uso ese, mejor.
Si quieres, apágase. Listo.
Ok, gracias.
¿Vas a usar ese?
Sí.
Pues te quito esto.
Ok.
Sí, me va a hacer feedback.
Ok. Okay, so can you hear me now, everyone? Yeah, okay, cool. So yes, I work at the Max Planck Institute. I am doing my PhD there, and this is my first year. And today I will tell you a little bit about how we image exoplanets and their formation. So first, the overview of my talk. I will give you a very quick introduction of the methods that we use to detect exoplanets. And then I will focus on high contrast imaging. And I will give you examples of how we use this method for exoplanets with AHLEP and with protoplanetary disks with WA of 6 and WSB 82. And finally, I will tell you about my ongoing work and the future of this. So, well, as you know, we can divide the detection methods in two main categories, like indirect and direct methods. Among the indirect methods, we have these main three. So the radial velocity, very quickly, is based on the fact that if a planet is orbiting a star, the star and the planet will orbit the common center of mass of the system. And this will translate in the star making a wobbling that we can detect. And from this, we can infer some properties of the planet. Another method, also a very famous one, is the method of transits, which is based on measuring the change in the flux when a planet passes in front of its host star. And as you can see, there is a drop in the flux, and then it goes back up. And from this, again, we can infer certain properties and characteristics of the planets. Then the other one is microlensing, which is based on the same principle as gravitational lensing. So here's us. We have a star with a planet in between us and a distant star, that which light gets lensed by this one. And if the planet that orbits this lensing star happens to be in a certain position, when we make the amplification curve, we will be able to detect it as a little blob here in this curve. So now, from all these methods, we have been able to detect thousands of planets, but they are all indirect methods, as I tell you. So the only direct method that we have right now is direct imaging. And well, this is literally taking a picture of an exoplanet, which is very cool, as you can see here on this little movie of the system HR 8799, where you saw the 4 planets moving. So this method targets basically young planets, because they have to be very still hot in order to be able to see them. They have to be at a certain distance from their stars, so we can also distinguish them. And they are mainly gaseous planets. So one of the advantages of this method is that we can actually see the whole architecture of the system. So we can see several planets at the same time. And this is very good. And another thing that we could see, in case there is a disk. If the star has a disk, we will also see it. And there have also been cases, as you may have heard, where we see not only the disk, but a planet within the disk, like still forming. To quickly recap, here is a mass period diagram with the exoplanets known up to the 1st of August of this year, with many of the methods that I mentioned and some additional ones. And here I highlighted the ones discovered with direct imaging that, as you can see, are indeed Jupiter-like planets, and they have the longest periods. So now, of course, direct imaging has some challenges to face, because first, well, the planets are really close to their stars in comparison to the distance from us to the stars. And they are also very faint. Even when they are young, they can still be up to 10 to the 9 times fainter. So what do we do in order to overcome these challenges? Well, we use something called high contrast imaging, which combines adaptive optics with the use of a coronagraph. And then we use post-processing techniques in order to look for the planets. So I will very briefly describe each of these concepts. Here I have a movie to illustrate what adaptive optics is based on. So here we have a non-adaptive optics image and a corrected image. So what you do is you take a reference star, you take the light of this star, and then you obtain a distorted wavefront that goes to the computer, and then you have a deformable mirror here, which will move a little bit in order to compensate for this deformation and give you a corrected wavefront, so that you can obtain an image like this one. So we combine these adaptive optics with the use of a coronagraph, which is basically a mask that we put in front of the star. And to illustrate some of the benefits of doing this, here I have on your left an image without the coronagraph of a star. So here we see the point spread function, the airy rings, and all the light of the star. And on the right, there is an image of the same star using a coronagraph. So you can see that most of the light of the star gets masked. And in this way, if there is something around the star, it would be easier to see it. Okay, so after we take the images with these two things, we need to do some post-processing. So there are many techniques to do this. And the one I use in particular is called angular differential imaging, or ADI. And the principle of this one is that, well, you take images of your star, and throughout your observation, the sky will rotate. So that if you have a planet, like on this example, the planet will be in different positions on each of your frames. And these type of frames will look like this one with the coronagraph, and these are some additional effects from the telescope and all the optics. And what we do is we take the median of all of these frames in order to get rid of the planet, so that we only get the light of the star. And then we take this median image and we subtract it from each of these frames, so that what we obtain are images that only contain, ideally, the signal of the planet. And then, well, we know the velocity at which the sky is rotating, so we can derotate each of these images and combine them, again, taking the median in order to get a higher signal to noise, so that instead of having this one where we have the planet but still some noise, we ideally get an image like this that only has the coronagraph and the signal of the planet. So now I will tell you a little bit about the instrument that we use to obtain the images. As Joel said, this one is SPHERE, which is located at the VLT. And this is an extreme adaptive optics system that has a coronagraph. Here we have a picture of the instrument, which is quite big, as you can see. And well, the scientific goals of SPHERE are to detect and characterize extrasolar planets. And for this, we use both imaging, low resolution spectroscopy, and polarimetry. And here I highlighted the three main subsystems, which this is an infrared dual imager and can also be used as a polarimeter. This is the integral field spectrograph, and this is a visual polarimeter. Now I will show you a couple of examples of famous planetary systems imaged with SPHERE. So here we have again HR 8799 with the 4 planets over here. So as you can see, they are very clear. And another famous one is 51 Eridani b with this very bright companion over here. So as you can see, SPHERE can really get very nice images of exoplanetary systems. And now I will tell you about the system that I studied for the first part of my PhD. This is called HLEP, over here behind the coronagraph. This is a solar type star at only 58 parsecs away. And as you can see here, we found 2 candidate companions near the star. And they are at around 12 and 23 AU from HLEP. And yeah, this is an infrared image from SPHERE after the post-processing using, sorry, I forgot to mention this is one of the several pipelines that you can use to do post-processing called Andromeda. But of course, well, it's not enough to detect the companions visually, but you also have to make some additional tests to see if these companions are actually bound to the system. So one of the things that one can do is an astrometry test, which is what we did. And for this, you need at least a second epoch. In this case, we took one from the Gemini Planet Imager, and we constructed this so-called corkscrew plot by taking the first epoch as the reference one. So here are the 2 candidate companions for HLEP. Then this gray line is the path that a background source would follow for the second epoch with respect to the first one. And here is the proper motion result, or the positions for the second epoch for these 2 candidate companions. So as you can see, unfortunately, what we found is that they are most likely background sources, as they fall very close to this point. But yes, but well, another thing that we could do with the data that we got from SPHERE was to extract the spectra for these sources to try to characterize them, maybe. So here they are. Yeah, it's low resolution spectra, so you can't see much. But one of the important things that we were able to not detect were methane absorption. So since there is no methane absorption, we can rule out that these are T-dwarfs. But in order to characterize them further and more definitely, we need more observations and more high-resolution spectra. Okay, but now I will move to the disk part of my talk. So here are some examples of protoplanetary disks imaged with SPHERE. As you can see, they are really pretty images as well. And disks can also be interesting because these 2, for example, have these spirals that we see here. And these ones have these cavities or rings. And And well, one of the causes, we believe that one of the causes of these structures can be planets that are carving these or disrupting the dust in the disks. So, of course, there are also some challenges in order to image disks. Again, the contrast and separation, because sometimes the disk can be cold, so it's a little bit faint, or they are small and very close to the star. So again, we use high contrast imaging and post-processing in order to retrieve these images. And we can image them both in scattered light and polarimetry in order to see the dust at the micrometer wavelength. So just to refresh your memory a little bit about polarized light, you know, polarization can arise from several processes, but the one that we are interested in is polarization by scattering, because if you have a disk, the light of the star passes through this disk medium and gets scattered by the dust. So from this, we can learn about the properties of the dust that scatter this light. And well, some other advantages of polarimetry is that you don't need a coronagraph in general, because usually the stellar light is mainly unpolarized, so you get rid of it without using a coronagraph. And this brings this other advantage, which is a smaller inner working angle, meaning that you can get much closer to the star because you don't have the coronagraph there. And well, again, since the light is scattered by this by the particles that compose the circumstellar material, then you can learn about it. And just to illustrate these advantages that I just mentioned, here we have two images of the same disk. On the left, we have the polarized light image, and on the right, we have the classical imaging. So here you can see a little bit the coronagraph, and well, that the brightness of the dust is different than here. But more importantly, that you can get much closer to the star in this case. And well, now I will present you the two objects that I've been studying and that I'm still studying. So this is WA-Ophiuchus 6. This is a protoplanetary disk surrounding a K6 type star. And what we have here is an image from ALMA, because we also use millimeter images to compare with SPHERE. This is a fairly young object, as you can see, 0.3 mega years. And well, from the ALMA images, we can see that it has some spirals over here, and then there is this outer ring. And then the other one is called WSB-82, which is a surrounding a T-Tauri star, and there is not a lot of information from this disk in the literature yet, so it has not been very well studied, but well, we are on it. And again, here is an ALMA image of this, where you can see this outer ring again and the cavity. And well, as I told you, these features are interesting because we think that maybe planets could be causing this, among other things, but I'm interested in planets. And well, one of the things that that I'm doing now is to compare the two images, the SPHERE images with the ALMA images, because here we have information from the micrometer dust grains, while here we have information from the millimeter dust grains. And with this, we can learn a little bit more about the architecture of these disks. So one thing that one can do is to overplot the, in this case, the SPHERE image, with the ALMA contours on top, to try to see if we can recover the same substructure in both. But this is still work in progress, so I know it's not perfect and you maybe don't see spirals here, but yeah, I'm working on it. And another thing that one can do is to compare the radial profiles, meaning to take the intensity as a function of the radius, in the disks. And here we have an example of TW Hydra, where here's the radial profile from Sphere and the radial profile from ALMA, that, as you can see, look very different because, yeah, they image different sizes of grains from the disk. But however, you can still see some features. So, well, this is the Sphere image, and you can perfectly see like the rings, the gaps, visually, and then in the radial profile. And with the ALMA image, you can see some features in the radial profile that correspond to the ones in the Sphere profile. But the interesting thing is to compare these things and then get a better idea of how the whole disk looks, like the inner and outer parts, and if it is flared or flat or all these things we can infer from this. And well, finally, about the future work and my current work is to, well, first I have to improve the data reduction for the polarimetry mode from Sphere in order to see if we can see closer to the star. Then I would like to also revise both data reductions from Sphere and from ALMA to see if there is something that we can improve. And then we will perform radiative transfer modeling to test all the theories that can be causing all this substructure that we see. So to see if there is maybe a planet doing something there, even when we don't see it, or what else could be. And as a side project, I will also continue analyzing interesting targets from the Sphere Shine survey as EHLEP in order to see if we can find an additional planet like this. So thank you for your attention, and if you have questions.
So are you working in any theoretical framework in regard to the structure of the disk? Because I can see gaps and stuff like that.
Yes.
I suppose if you study resonances in the system, you could maybe gain something from your study, right?
Yes. Yeah. So right now I am not working on the theoretical part, just on the observational and getting the radial profiles and the azimuthal profiles. But before we go to the modeling part, I will definitely have to consider all these resonances and more theoretical aspects of it. Yes. But that is indeed interesting.
How do you get the age of the protoplanetary disk?
The age?
Because
sorry. Okay, so that is mainly because of the moving group that the star belongs to. So it's not, you cannot determine
it's
the
an
age.
indirect
Yeah, exactly. Yeah,
measurement.
it's not a direct measurement.
Okay.
Yes.
More questions? No? So I have.
There is.
Okay.
Bueno, aquí. So the age of the disk, is there a constant about how old are the disks that used to have these structures, the circles or the rings and the arms, the spiral arms?
You mean if all the disks of this age have the same structures?
Yes, or the other way around.
Well, actually, in the survey that one of these disks, like the big survey that they belong to, they only found 3 that had this substructure, and they are all in Ophiuchus, so they are more or less like around the same age, and they only found 3. So it is not age dependent necessarily. We still don't know what this depends on. Yeah, but I'll try to find out. Yeah.
More questions? No? Well, I have one.
Yeah.
So how difficult is to estimate the astrometry? Because you don't have this central star, right? Because it's obscured by your mask.
So when you compute the position of your planet, what kind of errors do you put in there?
Okay, yes. Well, there is a way to estimate where the star is, but yeah, it has some errors always. So you just have to live with these errors and yeah, just assume them in the astrometry. But, as you can see, it's not that it was really close to the star. I mean, like even within the errors, you could see that these two sources were away, like background. Yes, yeah, but it's true that there is some error implied. So I think this takes more importance when you find that they are closer, and then you put more attention on the error. Yeah. So.
More questions? No? Well, if not, thank you very much, Samantha.
You're welcome.
It was a very nice talk.
Thank you.